So, let's talk about how to actually do science. And we're going to start with a question that might sound a little, well, familiar. Something you might have even wondered about in your own kitchen. All right, so think about this for a second. Have you ever noticed when a pori puffs up, why is one side always thinner than the other? It's such a simple thing, right? Something you see all the time. But you know what? That's exactly where a real scientific adventure begins.
And that right there is really the heart of it all. See, science isn't just about memorizing a bunch of facts. It's about that journey, the one that kicks off with those simple little questions. The whys and the hows, just like with our porridge.
This is a really big deal, actually. It's a total shift in how we think about learning. We're moving past just, cramming facts into our heads. The real goal here is to become an investigator, to learn how to find things out for yourself. You can almost think of it like leveling up, right? At first, you're just full of wonder, asking why about everything. Then you start to get it. Every answer you find just leads to another, even cooler question. And then you hit the best part. You start designing your own ways to find the answers. That is what investigation is all about. And this really shows you the before and after. We go from just kind of looking at the world, being curious, to actually grabbing a notepad, asking specific questions, and stepping into the role of a scientist. Okay, so if you want to be a great investigator, you need the right tools. But I'm not talking about lab equipment. I'm talking about a mindset. And there's this fantastic way to think about it, using roots and kites. This is such a cool idea. Think about it. The roots, they keep you grounded. They're all about careful, solid observation. What can you actually see and measure? But then you have the kite. And the kite, that's your imagination, your curiosity. It's all those wild what-if ideas that you let soar high into the unknown. So, where does the magic happen? Right in that sweet spot. The balance between what you can see, the roots, and what you can imagine, the kite. You absolutely need both. That's where the real discoveries are made. Okay, so what does this look like in the real world? Well, once you start wearing these investigator glasses, you'll see that the world is just overflowing with questions. They're literally hiding everywhere. I mean, we could dive into the unseen world of microbes. How do they work? How in the world do vaccines prepare our bodies to fight them? It's a tiny, invisible battlefield with a huge impact on all of us. Or think about the tech we use every single day. Why does an iron get hot? How does electricity turn into heat? These are questions about the fundamental energy that powers our entire lives. And then there are these huge invisible forces all around us. Why does a ball always fall back down? Understanding things like gravity helps us explain pretty much all motion, from tossing a toy to a massive hurricane. Or we can zoom way out and look at the whole planet. How do all the plants and animals and the environment itself all rely on each other? When you investigate ecosystems, you start to see that everything is connected in this beautiful, complicated web. All right, this all sounds great, right? But how do you actually start? How do you begin thinking like this, like right now? Well, the best part is, you're already equipped. You have everything you need to begin. Seriously, you don't need a fancy lab coat. You don't need a bunch of expensive gear. Your kitchen, it's one of the best laboratories on the planet. All you really need is that spark of curiosity, that little voice that asks, what would happen if? So let's circle back to our Puri mystery and put this into practice. First, you start with a clear question. What actually makes it puff up? Then you brainstorm all the things you could change, the variables, maybe the thickness, the type of flour, the oil temperature. Now, step 3 is crucial. You only change one of those things at a time. That's how you know what's causing the change. Then you just watch and write down what happens. And almost always, that leads to brand new questions, like, what if I poke a hole in it first? See, that's a cycle. That's real investigation. And now for my favorite part. Get this, even for something as simple as a pori puffing up, scientists today don't fully understand it. Isn't that amazing? The mystery isn't completely solved. It just goes to show you that science isn't some big book of finished answers. It's an ongoing story of discovery, and there were these incredible puzzles just waiting for us, everywhere. So what's the big takeaway here? It's that your curiosity is your superpower. The world around you, from your own kitchen all the way out to the stars, is just packed with mysteries. The only question is, what everyday mystery are you going to investigate next?
You know, there's this whole world, a bustling, living universe that's totally hidden from us. It's in every single drop of water, every pinch of soil, even in the air we're breathing right now. So, let's dive in and explore it together.
I mean, what if you could actually see it, this invisible world that's living all around you at this very moment? Just imagine shrinking down and seeing it all up close. What do you think you'd find?
And this isn't some sci-fi movie. It's real. It's the microscopic world, a whole ecosystem on a scale that's almost impossible to wrap your head around. So the big question is, how did we even find out about it? How did we first get a peek into this hidden universe?
Yeah, for pretty much all of human history, we had no idea this stuff existed. It took one game-changing invention to pull back the curtain and, well, change everything we thought we knew about life itself.
And it all started with something surprisingly simple, a piece of curved glass. People figured out a long, long time ago that it could make things look bigger. And over time, we just got better and better at making these lenses, more and more powerful, until eventually they became the very first microscopes. Basically, our first window into this invisible world.
So one of the first people to really peer through that window was this guy, Robert Hooke. He was a brilliant English scientist, but also an amazing artist. Back in 1665, he published this book called Micrographia, and it was packed with these incredible, super detailed drawings of things nobody had ever seen before.
When he looked at a tiny, thin slice of cork, he wrote that he saw it was made of many small, empty spaces. He said these little compartments reminded him of a honeycomb.
And he called these little boxes cells. And just like that, he gave a name to the fundamental building block of all living things. I mean, think about that. That one word, that one observation, completely changed the course of biology forever.
Now, at pretty much the same time, another guy, Antoine van Leeuwenhoek, over in the Netherlands, was making even better lenses. He was the first person to see tiny living things swimming around, actual bacteria, and even our own blood cells. It's no wonder they call him the father of microbiology.
Okay, so Hooke gave us the name cell. But what is a cell, really? What was it that he and Leeuwenhoek had stumbled upon?
Well, simply put, a cell is the basic unit of all living things. It's the smallest piece of you that's actually alive. The best way to think about it is like a brick. You know, you put a bunch of bricks together to build a wall. Well, you put trillions of cells together to build, well, you, or a giant whale, or the smallest little plant.
But of course, just like you have different kinds of bricks for different jobs, not all cells are the same. Let's take a look at two of the main types you'll find: plant cells and animal cells.
And right away, you can see some pretty big differences. Plant cells have this really tough, rigid cell wall that gives them structure. They've also got these green things called chloroplasts. That's what they use for photosynthesis, to make food from sunlight. And they usually have one giant vacuole for storing water. Animal cells? Nope. No cell wall, no chloroplasts. And if they have vacuoles at all, they're tiny and temporary.
Okay, so that makes sense for plants versus animals. But what about all the cells inside just one organism? Like, are all the cells inside you the same?
No way, not even close. A cell's shape is totally tied to its job. It's a classic case of form follows function. Take a look here. Muscle cells are long and spindle-shaped so they can contract and pull. But nerve cells, they have all these long, crazy branches to send signals all over your body.
And here's the cool part. These specialized cells don't just float around on their own. They team up. Cells form tissues. Tissues form organs, like your heart or your lungs. Those organs work together in organ systems, like your circulatory system. And all those systems together, well, that's what makes up an entire organism.
But here's what's really wild. Some living things, they just stop at that very first level. They're an entire, complete, living organism made of just one single cell.
We call these microorganisms, or just microbes for short. And yeah, the name kind of gives it away. They're so small you can only see them with a microscope, and they come in a few main flavors. You've got your bacteria, fungi, algae, and protozoa.
And the diversity here is just mind-blowing. You've got protozoa like an amoeba, which can move around on its own. You've got algae, which have that green chlorophyll just like plants. Fungi, like the mold you might find on old bread. And then bacteria, which are tiny and come in all sorts of shapes. Rods, spirals, spheres, you name it.
So, where do these little guys live? Honestly, a better question is, where don't they live? They are literally everywhere. In water, in the soil, in the air. They live in super extreme places like boiling hot springs and deep inside frozen snow. And, yep, you guessed it, there are trillions of them living inside your body right now.
So, okay, they're tiny and they're everywhere. But why does any of this matter? What kind of impact do they really have? Well, one of their biggest jobs is being nature's cleanup crew. Think about it. When stuff like leaves or old fruit peels get thrown out, what happens to them? Microbes, like bacteria and fungi, get to work. They eat all that waste, break it down into simpler stuff, and turn it into super nutrient-rich manure that makes the soil healthy for new plants to grow.
Seriously, without them, our planet would just be piled high with dead stuff. They are absolutely essential. They clean our environment, they help plants grow, they help us digest our food, and we even put them to work on purpose to make delicious things like bread, cheese, and yogurt.
So this invisible world, it isn't just floating around us. It's inside of us. It's a part of us. And it's what keeps our entire planet alive and running. So how does that change the way you see life? Something to think about, right?
Okay, so when you hear the word healthy, what's the first thing you think of? For a lot of us, it's probably just not being sick, right? But what if I told you that real health is so much more than just not having a cold? Let's dig into what it truly means to be healthy. You know, to really get what we're talking about, let's start with a story. It's about a young student and his experience. Well, it shows just how connected our minds, our bodies, and the world around us really are. So, picture this. A kid in grade 8, he's just moved to a brand new city. New school, his parents are super busy, and he doesn't have a single friend. In this sea of new faces, he felt totally, completely alone. And that's when things started to get weird, physically. First, he started getting these constant, just nagging headaches that wouldn't go away. On top of that, he couldn't sleep. He'd toss and turn all night, which just left him feeling exhausted and completely drained the next day. And then, the final piece. He started losing weight. It was undeniable at this point. His body was basically screaming for help. So what was going on? I mean, a doctor might check for a virus or some kind of infection, but the real problem? It wasn't a bug. It was his social life. Because he was so lonely, he started spending more and more time on his phone, trying to cope. But that just made things worse, creating this awful vicious cycle. It's a textbook example of that mind-body connection, where feeling lonely can actually trigger a physical stress response and give you real symptoms. And look, this kid's story, it's not just a one-off. It's actually a small piece of a much, much bigger picture. So let's zoom out for a second and look at the huge health challenges we're all facing today. Let's imagine we have this big, empty bulletin board, right? We're going to use it to map out what's really going on in our world, piece by piece. First pin on the board, and this one's a doozy. In India, 11.4% of the entire population is diabetic. To give you some perspective, that's over 100 million people. That's more than the entire population of a country like Germany. Just wow. All right, next up, another pin. More than a quarter of the population in India, 28.6%, is obese. And we all know that's linked to a whole bunch of other health problems. But it's not just about what we eat or how much we exercise. Nope, our environment has a massive role to play. The very air we breathe, it's become a public health emergency that affects every single one of us. And here's where it all circles back to that student we started with. All this extra screen time, it's not just making kids lonely. On a massive scale, it's connected to more obesity, sleep problems, and anxiety. Yeah, our bulletin board is looking pretty crowded and kind of scary, right? So when you see all these things pinned up together, from loneliness to pollution to diabetes, you start to realize our old way of thinking about health just doesn't cut it anymore. We need a new way to look at this. Which brings us back to that big question. Is being healthy just about not being sick? I mean, looking at our board, the answer seems pretty clear, doesn't it? It's a definite no. And this is where the World Health Organization comes in with a game-changing definition. They say health is a state of complete physical, mental, and social well-being. See that? It's not just about what you don't have, like a fever. It's about the positive presence of well-being in every part of your life. So what does that actually look like in real life? Well, a truly healthy person can handle tough situations. They get things done efficiently, they get along with people, and this is a big one, they actually enjoy their social life. It's the whole package. Okay, that sounds great, right? Complete well-being. But how do we actually get there? Well, for some answers, we can look to ancient wisdom that's understood this stuff for centuries. A lot of modern medicine is about treating symptoms. You get a headache, you take a pill. But ancient wisdom, like the traditional Indian system of Ayurveda, has a totally different take. It's all about balance. It doesn't see your body, your mind, and your environment as separate things. It sees them as one interconnected system. And that's the real difference, treating a symptom versus restoring your overall balance. So how do you actually find that balance? Well, the Ayurvedic approach is surprisingly down to earth. It starts with simple routines, following daily patterns, something called dinacharya, and adapting to the seasons, or rutucharya. It's all about syncing up with nature. Then you add in fresh, whole foods, regular exercise, and good, restful sleep. But it doesn't stop there. Keeping a calm mind with things like yoga and meditation is just as crucial.
All right, so we've gone from one student's story all the way to this huge global idea of well-being. What's the big takeaway here? What should you remember from all this?
It really boils down to this. Health isn't something you just have, it's something you do. It's an active practice. And you can build that complete well-being by focusing on these key things: eating good food, keeping clean, moving your body, getting enough sleep, and, of course, taking some time for mindfulness or meditation. These are the real pillars of a healthy life. And I want to leave you with one last thing to chew on. Just remember how connected our own health is to the health of the world around us. So we have to ask bigger questions. For example, as our planet changes, with climate change and everything, could we start seeing brand new diseases, things we've never even imagined? It's a big question, and it reminds us that our health is, without a doubt, the most valuable thing we have. There are these incredible, invisible forces all around us, shaping pretty much everything in our modern world. And it all starts with something simple: the silent, unseen flow of an electric current, a force with some seriously surprising effects. So let's kick things off with a question that might sound a little strange, but it's one that actually stumped scientists for ages. Can a totally normal wire, just like the ones in your walls, actually behave like a magnet? All right, check this out. It's a really simple setup. We've got a battery, a wire, and it's stretched right over a regular magnetic compass. Now, usually that compass needle just points north, right? But watch. The second we complete that circuit and let the current flow, the needle moves. It actually jumps to the side. What is going on here? That tiny little twitch of a compass needle, well, it was absolutely revolutionary. It showed us for the very first time this deep, fundamental connection between two of nature's biggest forces. Honestly, it changed everything we thought we knew about the universe. This whole phenomenon is called the magnetic effect of electric current. And what that really means is that any wire, any conductor at all with electricity flowing through it creates its very own invisible magnetic field. It's like the wire temporarily becomes a magnet just because of that flow of electricity. And the crazy part? This world-changing discovery was made completely by accident. Back in 1820, a professor, Hans Christian Ørsted, was just giving a lecture. He happened to notice that every time he turned on his electrical setup, a compass sitting nearby would twitch. That one single accidental observation, well, it unlocked a whole new era of technology. Okay, so if we know for a fact that electricity can create magnetism, well, that leads to a really cool question, right? Can we control it? Can we actually harness this force and make it do what we want? I mean, just imagine it. What if you could have a magnet that only works when you tell it to? One you could just flip on and off with a simple switch. That idea right there is the whole secret behind one of the most useful inventions ever, the electromagnet. And what's so brilliant about it is how simple it is. Seriously, you can make one with just a couple of things. First, you just wrap an insulated wire really tightly around an iron core, like this nail here. Then you connect the ends of that wire to a power source, like a simple battery. And voila, here's what happens. The second that current starts flowing through the wire, that ordinary nail becomes a magnet, strong enough to pick up all these paper clips. But here's the magic. You disconnect the battery, the current stops, and the magnetic field just vanishes. The clips drop. It's a magnet on command. Now, this isn't just some neat little science experiment. This super simple idea of an electromagnet, well, it can be scaled up to do some truly massive jobs.
Yeah, we're talking about taking that exact same principle, a coil of wire around some iron, and just making it huge. These giant electromagnets are the workhorses in scrapyards and factories, lifting tons and tons of metal, sometimes even entire cars, all with just the flick of a switch. But creating magnetic fields isn't the only trick up electricity's sleeve. Nope, it's got another side effect, a much, much warmer one, that you definitely experience every single day. You know how your phone charger or your laptop brick gets warm after it's been plugged in for a bit? That's it. That's the heating effect of electric current right there in your hands. As electricity pushes its way through a wire, it runs into resistance, kind of like friction, and that friction turns some of that electrical energy into plain old heat. And boy, have we put this effect to good use. It's the secret sauce behind so many of our household essentials. Think about it. The glowing red coils in your toaster, the burners on an electric stove, the element in your water heater, your iron, even your hairdryer. They all work because of this simple heating effect. So we've got magnetism and we've got heat, all from a current. But hold on, all of this needs a source of power. For all our portable gadgets, that source is the humble battery. So how does it actually turn a bunch of chemicals into electricity? It all comes down to some really clever chemistry. See, the basic building block of a battery is called a cell. And inside, you've got two different kinds of metal. Those are the electrodes. And they're sitting in a conductive liquid, which is called an electrolyte. It's the chemical reaction between all these parts that gets electrons moving, and that flow of electrons, well, that's your electricity. Now, these cells basically come in two main flavors. You've got your single-use batteries, where that chemical reaction can only happen once. When the chemicals are all used up, the battery's dead. Then you have rechargeable batteries, like the one in your phone, where plugging it in actually reverses the chemical reaction, letting you use it again and again. So there you have it. Just from the simple flow of electricity in a wire, we can create these invisible magnetic fields powerful enough to lift a car, and we can generate enough heat to cook our food and keep us warm. It's pretty amazing when you think about it. These two fundamental principles, the magnetic and the heating effects of a current, they are the invisible bedrock of our entire technological world. From tiny motors to massive cranes, they're working all around us, all the time. Learning to harness these forces was the first giant leap. And that leaves us with a really fascinating final thought. Now that we've mastered these invisible powers, what new forces will we discover and command next?
You know, every single moment of your life, you're in a constant dance of pushes and pulls. It's kind of like a silent conversation with the world around you. Today, we're going to make that invisible interaction visible. We're talking about force.
Just imagine you're on a bike, right? You can feel the wind fighting against you. It's a real physical push. Then you get to the top of a hill and start coasting down. You're not even pedaling, but this unseen pull just takes over, making you go faster and faster. These everyday feelings, they're our way into understanding one of the most fundamental ideas in all of science.
So to really get a handle on this, we're going to join two friends, Sonali and Ragini, on a bike ride that actually turns into a perfect little physics lesson. Their journey is going to show us the forces that shape our world every single day.
And bam, right away, Ragini feels it. It's this powerful, invisible push. The wind is working against them, and it's forcing them to pedal so much harder just to keep moving forward. So they're not just riding a bike, they're literally fighting against an unseen opponent. A force is at work here.
So what is this thing? Rajani felt a push from the wind, and later they're going to feel a pull that sends them flying downhill. Well, in science, both of these things, the push and the pull, are described by one single powerful word. And that word is force. At its core, it's just a push or a pull. Simple enough, right? But the really crucial part of that definition is interaction with another object. See, a force never ever acts alone. We'll get more into that in a second, but first, let's see what these forces can actually do. Okay, so we've got a name for it, but what does a force actually do? I mean, what's its impact on the world around us? Let's dig into the powerful effects of a simple push or pull.
A force is a total game changer for any object. Seriously, it can get something moving when it's standing still, it can stop something that's already moving, it can change its direction, or it can even change its actual shape. Let's see this in action.
Just look at this. That ball is a blur. It's moving so fast. But the fielder's hands apply a sudden, massive force, and in a split second, that ball's speed drops to zero. That's a force changing an object's speed.
Plain and simple. But a force doesn't just change how fast something's going. It can completely change its direction. A pitcher throws a ball one way, but the batter applies a force with the bat that sends it flying somewhere else entirely. It's the exact same idea that Sonali and Regini used when they applied a force to their handlebars to steer.
And finally, get this. A force can change an object's shape. You pull on a rubber band and it stretches. You squeeze a piece of dough and it flattens. All of these are just examples of a force causing a real physical change.
Okay, let's circle back to that key idea we mentioned earlier. Forces come from interactions. Now, this might sound a little abstract, but it's one of the most important things to understand. A force isn't something a single object has. It's a two-way street.
And it's pretty simple when you think about it. I mean, to push a table, your hand has to actually touch the table. For the wind to push Regini, the tiny particles of air had to collide with her and her bike. You just can't have a force without an interaction between at least two things.
So knowing that forces are interactions helps us start to sort them into different categories. And the most common, most intuitive types are the ones that need direct physical touch, the forces we can actually feel.
These are called contact forces. And yep, the name pretty much says it all. They're everywhere. Kicking a ball, lifting a box, pushing a door. All of those things need direct contact to happen. Let's look at one of the most basic types.
Every single push on the pedals from Sonali and Regini was a perfect example of muscular force. This is a contact force, and it's generated by the action of their muscles. It's how we, and pretty much all animals, physically move things in the world around us.
And it's not just our own muscles, right? For centuries, human civilization was literally built on the muscular force of animals. Everything from plowing fields with oxen to pulling carts with horses. It's a really powerful and fundamental tool.
Now, for another really important contact force. This is one Sonali and Ragini definitely felt on their ride. It's the force that always seems to be fighting you, always trying to slow you down.
We've all been there. You're riding or walking along, and suddenly the ground gets rough, and you have to work twice as hard to keep going. You're not going uphill, so what's pushing back? Well, that's the force of friction.
Okay, the key thing to remember about friction is that it's the ultimate opponent. No matter which way an object is moving, friction is always pushing back in the other direction. It's caused by the tiny, microscopic imperfections on two surfaces grinding against each other.
You know, in a world with zero friction, a rolling ball would just keep rolling forever. But here, in the real world, the constant interaction between the ball and the ground creates friction, which acts like a brake, and it gradually slows that ball down to a complete stop. So let's go back to our bike ride. We can now see this amazing battle of forces happening. You've got Sonali and Regini's muscular force pushing the bike forward, while the force of friction from the road and the air is pushing them back. It's a constant tug-of-war.
And that brings us to one last fascinating question. We get the push from their muscles, and we get the push back from friction. But what about that invisible pull that sent them speeding downhill without even pedaling? Well, that's a whole different kind of force, one that can act without touching at all. And that, well, that's a story for another time.
Pressure. It's this invisible force that's all around us, working in ways we don't always notice, but we definitely feel it. So today, we're going to pull back the curtain and make this unseen force seen. You know the feeling, right? You've got a heavy bag, and those thin little straps are just digging into your shoulder. It's awful. But then you switch to a bag with wide straps, same weight inside, and it feels so much better. What gives? Well, the answer to that little mystery is pressure. To see what I mean, let's meet Megha and her brother Pawan. Now, their bags have the exact same stuff inside, so they weigh the same. But look at them. Megha looks totally fine, while Pawan is clearly struggling. So what is going on here? Well, the secret isn't what's inside the bags, it's the bags themselves. More specifically, as you can probably guess, it's all about those straps. Here's the breakdown. Pawan's bag has these narrow straps, and they're focusing all of that weight onto one tiny spot on his shoulder. Ouch. But Megha's bag, it's got those nice broad straps that spread the very same weight out over a much larger area. That makes it way more comfortable. See, this isn't just some random life hack for picking a comfy backpack. It's actually a fundamental principle of physics. And that brings us right to the star of our show, the pressure principle. Okay, so what is pressure, really?
Well, the official definition says it's the force applied to a surface divided by the area it's spread over. The key thing to remember is it's not just about how much force you have, but how spread out or concentrated that force is. And it all boils down to this super simple, super powerful formula. Pressure equals force divided by area. That's it. This little equation explains so much about how the world works. From our backpacks to, well, you'll see. This quote really nails it. The smaller the area you're pushing on, the higher the pressure you get. That's exactly why Pawan's thin straps hurt. All that force is concentrated on a tiny area, creating a point of really intense pressure. And this idea isn't just for school bags. Nope. Once you get this, you are going to start seeing the effects of pressure absolutely everywhere. Think about a hammer and a nail. Why do we hammer the pointy end? Because that tiny little tip concentrates all the force from the hammer into a super small spot. That creates immense pressure, enough to pierce right through a piece of wood. Trying to hammer in the flat head? Yeah, good luck with that. The area is too big, the pressure is too low. It's the exact same principle behind a sharp knife. That super fine edge is a tiny, tiny surface area. So even with a little bit of force from you, it creates enough pressure to slice an apple. A dull knife, on the other hand, has a wider edge. It just squishes the apple because it can't generate enough pressure. Okay, so we've talked about solids like bags and nails, but what about liquids? Does the water in a glass push on the bottom? Does water even have pressure? Oh, you bet it does. Let's see how that works. All right, check out this simple experiment. We've got a pipe with a balloon stretched over the bottom. Now, let's pour some water in. What do you think is going to happen to that balloon? And boom, the balloon bulges out. That's not magic. That is visible pressure. The weight of all that water in the pipe is creating a force, and that force is pushing down on the area of the balloon, creating pressure that makes it bulge. Okay, this is where it gets really interesting. We've established that the water column creates pressure. So what do you think will happen if we add more water and make that column taller? Is the pressure going to change? And there's our answer. A much bigger bulge. This shows us something super important about liquids. The height of the column is what really matters. The taller the column of water, the more weight is pushing down, and the greater the pressure at the bottom. Now, this direct link between height and pressure isn't just some neat lab trick. It's actually used to solve a huge practical problem you probably see every single day. Ever wonder why water towers are so tall, or why those big water tanks are always on the roofs of buildings? It's not for the view. It's a really clever use of physics, and specifically liquid pressure. By putting the water way up high, that tall column of water creates a ton of pressure in the pipes below. And that high pressure is what gives you that strong, powerful stream of water when you turn on your tap. It's just simple physics doing all the heavy lifting for us. So let's do a quick recap. Pressure is just force divided by area. Simple as that. If you have a small area, you get high pressure. Think of that nail. If you have a large area, you get low pressure, like Mega's comfortable bag straps. And when it comes to liquids, height is everything. The higher the liquid, the greater the pressure. So pressure explains why a bag strap hurts your shoulder and how water gets to your kitchen sink. But this very same force also operates on a planetary scale. When you apply this principle to our atmosphere, differences in pressure can drive winds, create massive storms, and even spin up something as powerful as a cyclone. How does that happen? Well, that's a story for another explainer. You know, everything you can see and touch, the chair you're sitting on, the air you're breathing, it's all hiding this incredible secret. Today, we're going to pull back the curtain and see what the world is really made of. So, let's kick things off with a few simple questions, the kind you might not even think to ask, but they have some seriously deep answers. I mean, think about it for a second. Some things, like rocks, they just hold their shape. You can stack them up, no problem. But then you try to do that with water, and it just flows everywhere. What is going on there? And you see these little mysteries everywhere, right? Here's another one for you. Why does a balloon get heavier when you blow it up? I mean, air's invisible. You can't see it, but it's definitely got weight. To figure this all out, we've got to go deeper. A lot deeper. All right, time to play detective. To solve any mystery, you need clues, and our first clue comes from something really simple. Just taking an object and breaking it. So, Imagine you've got a piece of chalk. You can snap it in half, then break those halves into smaller bits, and you can keep going and going until you've ground the whole thing down into a super fine powder. Now here's the crazy part. Even when it's a powder, it's still chalk. Every single one of those tiny, tiny specks is still chalk. That kind of suggests that the original stick was just a massive collection of these identical little units, all packed together.
Okay, so that was our first clue. Now for clue number 2, let's investigate a little bit of kitchen magic. You know, what happens when you stir some sugar into a glass of water? You give it a good stir, and poof, the solid sugar crystals are just gone. You can't see them at all. But of course, if you take a sip, it's super sweet, so the sugar is definitely still in there. But where did it go? How is that possible? All right, we've got our clues, we've got the broken chalk, we've got the disappearing sugar, and believe it or not, they are both pointing to one single, incredibly powerful idea that just explains, well, everything. And here it is, the big reveal. Everything around us, the solid ground, the liquid in your glass, the gas you're breathing, all of it is made up of unbelievably tiny particles, so small you could never, ever see them. And scientists have a name for these little guys. Constituent particles. You can think of them as the fundamental Lego bricks that build up every single substance in the universe. And that solves our sugar mystery. The sugar didn't really disappear. It just broke down into its individual particles, which were so tiny they could slip right into the empty spaces that exist between the water particles. Pretty clever, huh? But wait, it gets even cooler. These particles aren't just floating around randomly. There are forces of attraction that pull them together. And the strength of these forces, well, that's the key to everything. So how does this one big idea, this idea of tiny particles and the forces between them, explain the 3 main states of matter we see every single day? You know, solids, liquids, and gases. You know, when you look at solids, liquids, and gases, the massive differences between them all boil down to just 2 simple things: how close the particles are to each other and how strong that attraction between them is. And as you'll see, the differences are huge. Let's start with solids. Here, the particles are packed together super, super tight, and those forces between them are incredibly strong. It locks them into place. They're basically in a microscopic mosh pit, vibrating like crazy, but totally stuck. And that's why a rock keeps its shape. Now, in a liquid, the particles are still pretty close, but the forces are weaker. It's like they're in a crowded room, able to shuffle around and squeeze past each other. This is exactly why water can flow and take the shape of any container you pour it into. And then you've got gases. The particles are like social distancing pros. They're super far apart, zipping around randomly with almost no attraction to each other. And that explains why a gas will always expand to fill every last nook and cranny of whatever space you put it in. Okay, get ready for one last detail that might just blow your mind. We've talked about the space between particles, but just how real is that empty space? Well, we can actually prove this space is real with a super simple test. Just take a syringe, pull the plunger back to suck in some air, then block the end with your thumb. Now, what do you think happens when you try to push the plunger in? And you can push it in, right? Easy. That's because you're not actually squishing the air particles themselves. You're just closing up all that empty space between them. Now try doing that with a syringe full of water. You can't. It's basically impossible because the water particles are already packed right up against each other. So what does that mean? It means that stuff isn't really solid in the way we think it is. It's actually made of these tiny little points of matter with a whole lot of empty space, just pure nothingness in between. So let me leave you with this. The next time you rest your hand on a table or touch anything at all, just remember, you're not really touching a solid thing. What you're actually feeling are the forces pushing back between the particles in your hand and the particles in the table. You're interacting with an invisible world of countless tiny particles all dancing in a vast ocean of empty space. Have you ever just stopped for a second and thought about what the world around you is really made of? Today, we're going to dive into the science of mixing, and we'll uncover the hidden combinations in, well, just about everything, from your lunch to the very air you breathe. All right, to get us started, I've got a little question for you. What on earth could a savory plate of food and a simple glass of water possibly have in common?
Well, the answer is they're both mixtures. And honestly, that's the big secret. Most of the world is a mix of something. It's all around us, in the food we eat, the water we drink, everywhere. So let's start by looking for the science that's hiding in plain sight. In the most ordinary places you can imagine. It's a pretty simple idea, but it's also incredibly powerful. Everything, and I mean everything around you, the air, your food, the clothes on your back, it's all something called matter. And here's the really cool part. Very, very few of these things are made of just one single substance. Nope, almost all of them are mixtures. Just different combinations of two or more things, all brought together. So that brings us right to the heart of it, doesn't it? When a scientist uses the word mixture, what are they actually talking about? Okay, so a mixture is when you combine two or more substances, and this part is absolutely key, they don't chemically change into something brand new. In a mixture, a peanut is still a peanut, even after you've tossed it into your poha. It keeps its peanutness. So the individual things you put in the mixture, we call those components. And they just hang out together, they don't react with each other. Plus, you can mix them in any amount you want, a tiny pinch of salt or a whole spoonful. It doesn't matter. It's still a mixture. Now here's the thing. Not all mixtures are created equal. They basically fall into two main camps, and the difference is actually really easy to spot once you know what you're looking for. It really just boils down to one simple thing. Can you see the different parts? In what we call a non-uniform mixture, you can totally see the different bits and pieces. But in a uniform mixture, everything is blended so perfectly that it just looks like one single substance. Think about it like this. In a sprout salad, you can easily point out the sprouts, the onions, the tomatoes. That's non-uniform. But once you stir some sugar into a glass of water, it just disappears, right? You can't see the individual sugar crystals anymore. That is perfectly uniform. All right, let's dive into our first case study. It's something that's literally all around us every second of the day, but we can't even see it. We're talking about air. Yep, the air we're all breathing right now is a perfect example of a uniform gaseous mixture. It's mostly nitrogen and oxygen, with just a little sprinkle of other gases like argon and carbon dioxide, all mixed together seamlessly. Okay, but wait a minute. If it's all invisible, how do we know that those other components are actually in there? I mean, how can we prove that something like carbon dioxide is part of this mixture we call air? Well, there's actually a really neat and simple experiment we can do. First, you make something called lime water, which is just a clear liquid. Then you just leave it out, exposed to the air. And you wait. And boom! There's your proof. The totally clear lime water starts to turn milky. Why? Because the stuff in the lime water reacts with the carbon dioxide from the air, and it creates these tiny, white, solid particles. It's a visible reaction that proves an invisible gas is really there. How cool is that? Okay, so mixtures aren't just things that happen in nature or in the kitchen. We actually use them to build our world. Let's take a look at some solid mixtures that have literally shaped human history. Just take a look at these everyday kitchen utensils. Chances are, a lot of them are made from stainless steel, brass, or bronze. And guess what? None of those are pure elements found in nature. They're all incredibly useful solid mixtures that we created. The fancy scientific name for this kind of mixture is an alloy. It's a uniform mix that has at least one metal in it, and the components are blended so well together, they look like a single, brand new material. For example, brass, that's just a mix of copper and zinc. Bronze is what you get when you mix copper and tin. And that shiny stainless steel, it's a mixture of iron, chromium, and nickel. By combining these, we create materials with amazing new properties, like the incredible rust resistance of stainless steel. All right, to wrap things up, I want to talk about a word we throw around all the time, maybe without thinking too much about its scientific meaning, and that word is pure. You see, what you or I might call pure in everyday conversation, well, it's often something totally different from what a scientist would call pure. It's like there's a huge gap between the grocery store aisle and the science lab. See, in science, for something to be pure, it has to be made of only one type of particle. That's it. So that carton of pure milk in your fridge, I hate to break it to you, but it's actually a super complex mixture of water, fats, proteins, sugars, you name it. Same goes for ghee or spices. Scientifically speaking, they're mixtures. And that leaves us with one final thought I want to leave with you. The next time you're shopping and you see a label that says pure, just take a second, think like a scientist, and ask yourself, what's really in there? What does that word truly mean?
Welcome to our explainer on the amazing world of solutions and density.
You know, have you ever stopped to think about that? When you make a drink, like lemonade, why does every single sip taste identical? It's not like one sip is super sugary and the next is all sour, right? Well, that's no accident. It's all about science.
And the answer really comes down to how things mix. See, on the left, you've got a perfect blend, what we call a solution. Everything is distributed so evenly you can't tell the parts apart. But on the right, with the sand, well, not so much. The sand just sinks. That's a totally different story. This difference is exactly what we're going to dive into.
So, to really understand what's going on, we need to know the basic players. Let's break down the 3 key building blocks of any solution.
First up, you've got the solute. Now, this is just the fancy word for the thing that gets dissolved. It's the sugar in your tea, the salt you put in water. Basically, it's the ingredient that seems to vanish.
And then, of course, you need the solvent. This is the stuff that does all the heavy lifting. It's what's doing the dissolving. For so many things in our daily lives, the solvent is just plain old water.
And here's the magic formula. You take your solute, add it to your solvent, and boom, you get a solution. It's that simple. Solute plus solvent equals solution. This little equation explains a ton about the world around us.
But what's happening on a level we can't even see? Well, the solute particles don't actually disappear. Instead, they spread out perfectly among the solvent particles, just like you see here. This incredible, even distribution is the secret sauce. It's why every sip of that lemonade tastes exactly the same.
Okay, so we know things can dissolve. But is there a limit? Can you just keep adding sugar to your tea forever and ever? Let's find out what happens when a solution basically says, all right, I'm full.
It's a really good question, isn't it? I mean, if 1 spoonful of salt dissolves, why not 100? But as you've probably seen for yourself, there's always a point where it just stops working.
And you can actually prove this to yourself with a super simple experiment. Just grab a glass of water and start adding salt, 1 spoonful at a time, stirring as you go. For the first few spoons, it'll disappear like magic. But if you keep going, something changes.
At the beginning, your water will look like this. Perfectly clear. This is what we call an unsaturated solution. All that means is that it can still dissolve more salt. You could say there's still room at the molecular party.
But eventually, you'll hit this point. No matter how much you stir, that salt just piles up at the bottom. The party is officially full. There's no more space. This is what we call a saturated solution. It has reached its absolute limit. And this limit, this full point, has a scientific name. It's called solubility. It's the maximum amount of a solute that can possibly dissolve in a solvent under specific conditions. And notice that little mention of temperature? That's a huge clue for what's coming next.
So, what if we could change that limit? What if we could bend the rules of solubility? Well, it turns out there's a huge X factor that changes the whole game: temperature.
And this is where it gets really fascinating. For solids like sugar or baking soda, heating things up helps. The hotter the water, the more stuff you can dissolve in it. But for gases, it's the complete opposite. The colder the water, the more dissolved gas, like oxygen, it can hold. That's super important for all the fish that need that oxygen to breathe.
Okay, so we've covered what happens when things mix together. Now let's switch gears and tackle a new puzzle. Why do some things float and others sink?
Seriously, think about it. Sawdust and sand are both just little bits of solid stuff. You drop them in water, and one bobs right on top, while the other goes straight to the bottom. What's the hidden property at play here?
And this is a perfect example of why just saying something is heavy or light doesn't work. I mean, a giant tree log can float, but a tiny little pebble sinks. So clearly it's not just about weight. We need a better concept to explain this.
And that special property is density. When we say that a block of iron feels heavier than a block of wood of the very same size, what we're really talking about is its density.
So what is density? Well, it's actually pretty simple. It's just a measure of how much stuff or mass is crammed into a certain amount of space or volume. Something like iron has high density because a lot of matter is packed into a small area. And something like wood has low density because there's less matter in that exact same amount of space.
So let's quickly recap what we've learned. A solution is a totally uniform mixture. Solubility tells us the absolute limit of how much can be mixed in. We saw how temperature can totally change that limit. And finally, density is the key that unlocks the mystery of why things float or sink.
And these ideas are not just in a textbook, they are everywhere. Density is the reason a massive steel ship can float, and it's why a hot air balloon can rise into the sky. So the next time you see something float or dissolve, just think about these amazing invisible forces at work. What other scientific principles are shaping your world right now without you even realizing it?
Today, we're tackling the mystery of curved mirrors. You know that feeling when you look into a mirror and the person staring back just doesn't quite look like you? Well, we're going to figure out how curved mirrors pull off that trick, bending and twisting reality right in front of our eyes.
Okay, picture this. You're at a science museum or a carnival funhouse. You step up to one of those wacky mirrors and bam, your head is suddenly gigantic. Or your friend standing next to you is completely flipped upside down. It's weird, right? It's disorienting and it makes you ask a pretty basic question.
Yeah, why do these curved surfaces create such strange and distorted reflections? I mean, it's a world away from the normal flat mirror you use every single morning.
Well, believe it or not, the key to solving this whole mystery is probably sitting in your kitchen drawer right now. I'm talking about a simple, shiny spoon. If you have one, go ahead and grab it. Look into the bowl part, the side that curves inward. See that? Your reflection is totally upside down. Now flip it over to the back, the part that bulges out. All of a sudden, you're right side up again, just a little smaller.
So what's going on here?
Well, that one object is actually behaving like two totally different kinds of mirrors. We're not talking about your everyday flat mirror anymore.
We've just entered the world of spherical mirrors. Now, that term might sound a little complex, but the idea is actually super simple. Just imagine a giant hollow sphere made of glass. If you cut a piece out of it, that curved section, that's a spherical mirror. So, first up, you've got the concave mirror. This is where the surface curves inwards, just like the inside of that spoon. And the easiest way to remember it, it forms a little cave that you can look into. And the opposite of that is a convex mirror. This one bulges outwards, just like the back of the spoon. It's pretty straightforward. Concave, caves in. Convex, bulges out. So the big question is, how does this one simple difference, curving in versus bulging out, completely change the image we see in the reflection? Okay, this is where the real magic is. A concave mirror is kind of the wild card. It can make things look bigger, smaller, or even flip them upside down, and it all depends on how far away the object is. But a convex mirror, it's way more predictable. It always shows a smaller, upright image every single time. And this just shows it perfectly. Look at this little toy Dalmatian. In the concave mirror on the left, it's flipped completely upside down. But over in the convex mirror on the right, it's perfectly upright, just a little smaller. It's the exact same object, creating two totally different realities. And that is the power of the curve. Think about your regular bathroom mirror, a plain mirror. It doesn't matter if you're close up or far away, you always look the same size, and you're always upright. But with these spherical mirrors, your distance changes everything.
So this is way more than just a funhouse trick or a kitchen experiment. These mirrors are all around us, engineered for some very specific and very important jobs. So, where are they hiding in your everyday life?
All right, let's start with concave mirrors. Because they can magnify things, they're perfect for shaving mirrors or makeup mirrors. It's also why dentists use them to get a really good look at your teeth. But they can also focus light. That shiny bowl shape behind the bulb in a flashlight or a car's headlight, that's a concave mirror, gathering all that light and shooting it forward into one powerful beam. Now, I'm pretty sure you've seen this phrase before. It's printed on almost every passenger side mirror on a car. But have you ever actually stopped to think about why it's there?
Well, the reason for that warning is that the mirror isn't flat. It's a convex mirror. And that little phrase is a direct result of the physics we just saw with the back of a spoon. So why would we use a mirror that messes with how far away things look? Well, there are two huge safety reasons. First, the image is always upright, which is, pretty important when you're driving. And second, by making everything smaller, the convex mirror gives you a much, much wider field of view. It helps you see into your blind spots. It's a trade-off. You see more of the road, but things look just a little bit farther away than they really are.
So you see, from something as simple as lighting up a dark path to something as crucial as safely changing lanes on the highway, these clever little curves are constantly at work, shaping our perception of the world.
It kind of makes you wonder, right? If a simple curve in a piece of glass can so completely change what we see, what other details, what other perspectives are we missing out on just by looking at things from one single straight-on point of view?
Have you ever wondered how we, as humans, first figured out how to measure time? I mean, before any clocks, before calendars even existed. Well, we looked up. The answer was written in the sky. So let's dive into that story and see how the cosmos became our very first clock. You know, it all starts with something you've probably seen 100 times, seeing the moon just hanging out in the sky during broad daylight. It seems totally normal, but that one simple observation actually sparks a huge question, right? If the moon is this giant ball of rock up there, why does it look different all the time? One night it's a tiny sliver, another it's this huge, bright circle. What's going on? Well, that's the big mystery we're going to solve. Okay, so before we get to the why, we have to understand the what. We've got to look at the pattern itself. It's the super predictable, repeating cycle of the moon's appearance, a rhythm our ancestors knew like the back of their hand. And here it is, the whole show. Over about a month, the moon goes through this full performance. It starts out invisible, grows to a full circle, and then fades away again, back to nothing. Every single month, like clockwork. So, when that bright lit up part of the moon seems to be getting bigger every night, we call that the waxing period. It's growing. And you guessed it, when that bright part starts to shrink and get smaller, that's the waning period. That's the second half of its monthly trip. Now, this whole cycle is really held up by two main events. You've got the full moon, or Purnima, when we see that complete glowing circle. And on the total opposite end, you have the new moon, or Amavasya, which is when the moon is totally invisible to us down here. All right, so we know what happens, but why? The secret isn't that the moon is actually changing its shape. Nope. It's all about a cosmic dance between the sun, the earth, and the moon. It really is just a matter of perspective. Our perspective. Okay, this is the most important part to get. The moon doesn't make its own light, right? It's just reflecting sunlight. So at any given moment, the sun is lighting up exactly half of the moon. Always. One half is bright, one half is dark. So those phases we see from our backyards, that's not the moon changing. It's just how much of that sunlit side we can see from our vantage point here on Earth as the moon orbits around us. See, as the moon makes that month-long trip around our planet, the angle between it, us, and the sun is constantly changing. And that angle, well, that angle is everything. And this just makes it crystal clear. When the moon is between us and the sun, we're looking at its dark side. That's a new moon. When we're between the sun and the moon, we see the whole lit up face, a full moon. Everything else is just in between. Simple as that. Now hold on. Let's bust a huge myth right now. The phases of the moon are absolutely 100% not caused by the Earth's shadow. That's a totally different thing, and it's way more rare. When the Earth's shadow does fall on the moon, we call that a lunar eclipse. It's a really special alignment that can only happen during a full moon, and it has nothing to do with the regular monthly cycle of waxing and waning. So why is this so important? I mean, who cares about waxing and waning? Well, this predictable, reliable cycle was one of the biggest discoveries in human history. It was our very first clock. That full cycle from one full moon to the next takes about 29.5 days. This became the steady, dependable tick-tock of a giant clock in the sky. It gave all of humanity its first real way to measure time longer than a single day. And just like that, our whole system of time was born from the sky. The Earth's spin on its axis gave us the day. The moon's cycle around the Earth gave us the month. And the Earth's big journey around the sun gave us the seasons. And of course, the year. So, early civilizations built their calendars around this. They'd track 12 of these moon cycles, or 12 moonths, you could say. And that was a year. The thing is, this lunar year was only about 354 days long, which, you can imagine, caused some headaches when trying to line it up with the solar year of the seasons. You know, this connection to the sky, it's not just ancient history.
It's a shared heritage that connects all of us. No matter the culture, our ancestors were all astronomers, looking up at the same sky. And you can find proof of this careful observation everywhere. Take this quote from the ancient Indian text, the Taittiriya Samhita. It shows a perfect understanding of how the sun appears to move across the sky with the seasons, knowledge that was absolutely vital for farming and for life itself. Yeah, this wasn't just some hobby. Tracking the heavens was essential for survival and for culture. It told you when to plant your crops, when to harvest, when to hold festivals. It gave our ancestors a sense of order in the universe, all based on the predictable rhythm of the sky. So the next time you look up at the moon, just remember, you're not just seeing a lump of rock. You're looking at our planet's oldest, most faithful clock. And it kind of makes you wonder, right? How different would our calendars, our festivals, our whole idea of time be if the rhythm of our night sky had been different from the very beginning?
Today, we're going to dive into the incredibly intricate connections that hold our natural world together. We're exploring that delicate balance of, well, how nature actually works. So let's get right into it. First up, a crowded path. We're starting with a real and growing conflict, a point of friction where the human world and the animal kingdom are colliding.
Just take a look at this scene. You've got a huge herd of elephants walking right past a railway line, right next to a town. Now, this isn't just some random encounter. It's actually a symptom of a much, much larger problem. So the big question is, why is this happening?
Well, the short answer, it all comes down to survival. In parts of India, these massive animals are literally being pushed into human spaces, looking for the very basics, food and water, that are becoming harder and harder to find in their own homes.
So what's behind this scarcity? The root causes are pretty clear. Their forest habitats are shrinking, the plants they eat are disappearing, water holes are drying up, and of course, deforestation for things like roads and buildings is just speeding the whole thing up. To really get what's going on here, we kind of need to zoom out and look at the fundamental building blocks of any environment.
That brings us to Section 2, Nature's Building Blocks. To understand what's happening to the elephants, we first have to deconstruct how their environment, and really any environment, is put together.
You know, everything starts with a habitat. It's a simple idea, really. A habitat is just the natural home for an organism. It's the place that provides everything it needs to survive.
And inside every habitat, you've basically got two kinds of components. First, you have the biotic parts. That's all the living stuff, plants, animals, you name it. Then you have the abiotic parts, the non-living things, like water, sunlight, and the soil. And here's the thing, you absolutely cannot have one without the other.
Think about it. A forest and a pond are totally different habitats, right? Each one is defined by its own unique mix of living, biotic factors, like the trees and the fish, and the non-living, abiotic stuff, like the amount of sunlight or the temperature of the water. All right, Section 3, a community of beings. So, we've got the basic parts down. Now let's see how all the living things, the biotic elements, organize themselves inside their habitat. The first level of organization is what we call a population. This is just a group of the same kind of organism living in the same place. So think of all the fish in that pond, or maybe all the oak trees in a forest. That's a population.
Now, when you take all those different populations that are living and interacting together, the fish, the frogs, the plants, the insects, you get what's called a community. It's basically the entire collection of life in that one spot.
So if we look back at our pond, we can see it's so much more than just water, right? It's a bustling community. You have a population of fish, a population of frogs, a population of water lilies, all sharing that space and constantly interacting.
Okay, now for one of the most critical ways they all interact, the flow of energy. Or, to put it simply, who eats whom.
The simplest way to picture this is a food chain. You've seen this before, right? Energy starts with a producer, like grass. That gets eaten by a consumer, like a hare, which then gets eaten by another consumer, like a fox. It's a nice, neat, straight line.
But nature is almost never that simple. I mean, a fox doesn't only eat hares, and hares aren't only eaten by foxes. In the real world, all these little food chains get tangled up into a much more complex and messy food web.
This brings up a really fascinating question. Just how deep do all these connections go? I mean, it might sound a little crazy, but could something like having fish in a pond actually help flowers grow on the land nearby?
Believe it or not, the answer is yes, and it is fascinating. Researchers found this incredible chain reaction. It all starts in the water. Fish eat the dragonfly larvae. Okay, so that means fewer adult dragonflies are flying around. Why does that matter? Well, it turns out dragonflies eat pollinators, like bees. So, fewer dragonflies means more bees can survive. And of course, more bees means more pollination for all the flowers on the shore.
So, there you have it. Fish in a pond can, indirectly, help nearby flowers thrive. It's just a powerful, real-world example of the invisible and often totally unexpected links that hold an entire ecosystem together.
Okay, Section 5, when the system breaks. Now that we understand these hidden connections, let's go all the way back to the elephants we started with.
Looking at this image again, we see it with new eyes now, don't we? This isn't just a group of animals, it's a population whose habitat, its forest home, is being broken down. The abiotic factors like water are disappearing, and the biotic factors like plants are scarce. And that's what's forcing them into conflict with the human community nearby.
This quote really just says it all. This chain of events shows how closely nature's elements are connected. The story of the elephants isn't some isolated event. It's a chain reaction, and it's caused by a breakdown in their ecosystem.
So what's the big takeaway here? Well, it's that every habitat is a complex system of living and non-living parts, all connected in this delicate web. And the really crucial point is that tugging on just one part of that web can send unexpected ripples through the entire system, just like the fish and the flowers.
And that leaves us with one final, pretty important thought. We just saw how the presence of one species, the fish, could have a surprising positive impact on something that seemed totally unrelated, like flowers.
So the question we really have to ask ourselves is this. If adding one element can do all that, what happens to the whole system when you pull just one single thread from this incredibly intricate web?
You know, when you think about it, the universe is just packed with planets. Billions, maybe even trillions of them. But so far, only one looks like this. So what's the deal? What makes Earth so special, so perfect for life? All right, let's get into it. I mean, just look at our own solar system. It's full of these empty, rocky worlds and giant balls of gas. But then there's Earth, just buzzing with life. I'm talking everything from the tiniest little microbe to the biggest blue whale. So what is Earth's secret sauce? What's the secret? Well, the first piece of the puzzle, the first clue, is understanding just how unbelievably fragile this whole setup is. Seriously, everything you see, everything alive, it's all packed into this incredibly thin layer on the surface of our planet. Okay, here's a great way to think about it. Imagine the Earth is an apple. Now, the entire place where life exists, we're talking from the bottom of the deepest ocean trench all the way up to the tip of Mount Everest. That whole zone would be no thicker than the skin of that apple. Just the skin. That thin, delicate layer, that's it. That's our entire world. So to really get a feel for how perfectly balanced that little layer is, we got to take a road trip. Let's take a quick look at our neighbors, Venus and Mercury. You'll see pretty quickly what happens when things aren't quite so just right. Okay, check this out. Mercury is the closest planet to the sun, so common sense says it should be the hottest one, right? Well, nope. Venus, which is farther away, is an insane 450 degrees Celsius. That's literally hot enough to melt lead. And then there's us, Earth, sitting at a pretty comfy 15 degrees. So what in the world is going on here? So yeah, the answer isn't as simple as just being close to the sun. The real secret, the total game changer, is something we have that Mercury doesn't, and Venus has way too much of, the atmosphere. Think of a planet's atmosphere like a blanket. It lets the sunshine in to warm everything up, but then it holds on to some of that heat, trapping it so it doesn't all just escape back into the freezing cold of space. And this whole process, it's called the greenhouse effect. Now, on Venus, this effect has gone completely off the rails. Its atmosphere is super thick with carbon dioxide, and it traps so much heat that the whole planet has turned into a giant oven. But here on Earth, our greenhouse effect is balanced perfectly. It keeps our world warm and cozy, just right for life to do its thing. So, okay, a balanced atmosphere is a huge deal, absolutely crucial. But it's not the only thing on the checklist for life. The very first thing you need is just being in the right place at the right time. You know, location, location, location. And scientists have a name for this perfect neighborhood. They call it the habitable zone, but you've probably heard its more famous nickname, the Goldilocks zone.
It's that sweet spot, that perfect distance from a star where it's not too hot, not too cold, but, you guessed it, just right. So why is this zone so important? What's the big deal? Well, it all comes down to one thing: liquid water. See, in this zone, water can stay liquid. If we were any closer to the sun, our oceans would just boil away. Poof, gone. Any farther out, and they'd be frozen solid. And as far as we know, liquid water is absolutely essential for life. But wait, there's more. Location isn't the whole story. Turns out a planet's size also has to be, you guessed it, just right. Yeah, it's all about balance. If Earth were a lot smaller, its gravity would be way too weak to hang on to our atmosphere. All our air would just float away into space. That's pretty much what happened to Mars. On the flip side, if Earth were way bigger, its gravity would be so strong it could literally crush the bones of most living things. Talk about a tough commute. So, because we're this perfect, just right size with the perfect amount of gravity, we get to have this amazing life support system. Our atmosphere doesn't just give us the oxygen we breathe. It also has this incredible built-in shield, the ozone layer. And that layer blocks the sun's most dangerous UV rays, basically acting like a planetary sunscreen.
Okay, let's recap. We've got the perfect location, the perfect size, and the perfect atmosphere. But there's one last crucial piece of the puzzle. It's a powerful, completely invisible force field that's protecting us right now.
Believe it or not, our planet is basically a giant magnet. Deep down in its core, there's a bunch of molten iron swirling around, and all that movement generates a huge magnetic field that stretches way out into space. And this magnetic field has a super important job. See, space is filled with nasty, high-energy particles flying off the sun and from deep space. As they come screaming towards Earth, our magnetic field steps in like a bodyguard, deflecting almost all of that dangerous radiation. Without that shield, those particles could literally blast our atmosphere away. So there you have it, the secret recipe for a planet teeming with life. It's not just one thing. It's this beautiful, delicate dance of 4 key ingredients all working together. You need the right distance from the sun for liquid water. You need the right size to hold onto an atmosphere. You need that atmosphere to have stuff like oxygen and ozone. And finally, you need that magnetic shield to protect the whole shebang. So the next time you see a picture of Earth, our blue marble, remember, you're not just looking at some rock with water on it. You're looking at the winner of an incredible cosmic lottery. A place where all the right conditions came together perfectly to turn a dead rock into a vibrant, living world.
Which brings us to one final mind-bending thought. We know the recipe that worked for us here on Earth. But is it the only recipe? As we keep exploring space, it's a huge reminder that we don't have all the answers. Science is always moving forward, so you have to wonder, what other secrets, or even what other kinds of life, are waiting to be discovered out there in the vastness of space?